Hi everyone, my name is Brian O'Connor, and I'm the Stratum project lead at Open Networking Foundation. Today, we'll be talking about ONF's open source solutions that enable data center interconnect and broadband access. And we've got a number of folks from ONF who will be presenting during this webinar. I'd like to start today with just a high-level view of ONF's project portfolio areas. ONF started in the SDN infrastructure game with OpenFlow and a lot of infrastructure-related projects. We've also expanded our portfolio largely through Cord to include edge cloud infrastructure, as well as mobile and 5G solutions and broadband solutions. Diving a level deeper, we can see the ONF projects that make up these solution architectures. At the foundational levels, we have ONOS, the SDN controller, we have Stratum, a switch OS, and we have P4, a programming language for defining data plane programming. We also have Trellis and ODTN. Trellis is an application suite that enables fabric connectivity in the data center, and ODTN is for optical disaggregated networks for both packet optical transponders as well as the OLS systems and ROADMs. Moving up the stack, we have Cord and XOS, which are our cloud infrastructure projects. And then going up even further in the stack, we have our broadband solution called Seba and our mobile solution called Ether. In today's webinar, we'll be focusing on these two areas. First, we'll be talking about the SDN infrastructure, specifically how Trellis and ODTN are built on top of ONOS and Stratum. And we'll also be talking about Seba, a use case that's enabled on top of this platform. We'll conclude today's webinar by talking about testing at the SDN infrastructure level. And if you're interested in Ether, we did a webinar last week, and the video is available on ONF's website. Looking at today's agenda, we have 3 parts. The first part will be looking at our production-grade P4 programmable SDN fabric. By this, we mean we're taking Trellis, Stratum, ONOS, and ODTN and bringing them together for the first time. We'll also be talking about Stratum's new support for CASSINI, which is a packet optical transponder, as well as Stratum's new support for Broadcom's OpenNSA SDK. Next, we'll be talking about a new use case that's enabled by P4 and the P4 fabric. And by this, we mean we're taking Seba, ONOS, and Stratum and bringing them together. We'll also be talking about our software-defined BNG for the access network as part of this use case. Lastly, we'll be talking about testing, deployment, and certification. We'll be talking about TestVectors, which is a black box system test framework for Stratum devices, and how that plugs into ONF's CI/CD pipeline for Stratum. And lastly, we'll be introducing ONF's new continuous certification program for hardware devices like Stratum-based boxes. Let's jump into our first demo. This demonstration is designed to showcase ONF's production-grade P4 programmable SDN fabric. In this demonstration, we're going to be pulling together many ONF projects. For example, we will be using the Stratum switch operating system to power our data plane. We'll be using the ONOS controller as our network operating system and control plane, and we'll be using the Trellis and ODTN SDN application suites. In this demo, we'll be adding a lot of new capabilities to our previous Trellis and Stratum and ODTN demonstrations. First, we'll be showcasing Stratum's Broadcom implementation and showing how it has been extended to support Trellis. This involved extending the Broadcom pipeline to include MPLS and a few other Trellis data plane features in Stratum, as well as in ONOS. This pipeline description is designed for Broadcom Strata XGS switches, but should also be portable to the Broadcom Strata DNX switching line in the future. These enhancements make Stratum an attractive option for Trellis users. Second, with recent contributions from PLVision, Edgecore, and ONF, Stratum now supports Edgecore's CASSINI packet optical transponder, which contains a Broadcom Tomahawk Plus switching ASIC. We can now use these devices as part of the Stratum fabric, enabling them to serve dual purpose as MPLS forwarders and packet transponders. This is the first time the device has been used in both roles simultaneously, and it represents an important milestone towards unifying ONF's Trellis and ODTN reference designs. For operators, this integration equates to reduced overhead, power, and space without compromise. Third, we'll be showing how Trellis and ODTN can be run on the same ONOS cluster, and this is the first time that's ever been done. Last, and certainly not least, we're going to be showcasing how Stratum now offers users a choice between Broadcom's OpenNSA and SDK-LT. The addition of OpenNSA will pave the way for additional ASIC support in the Broadcom Strata XGS, Trident and Tomahawk, and Strata DNX, Qumran, and possibly Jericho families. OpenNSA directly exports functionality from Broadcom's SDK, which is used in production by some of the largest operators in the world. Let's first talk about Stratum on CASSINI. Stratum is the first open source switching operating system for CASSINI, which is a packet optical transponder with a merchant silicon switching ASIC, as we just mentioned. The optical capabilities are being managed through open config models and programmed using GNMI. And we've integrated CASSINI as a native Trellis spine, meaning we have layer 2 through layer 4 control from the ONOS control plane. And this is a capability that's made available to us via the Tomahawk ASIC that's on the box. This is a project from the Telcom Infrastructure Project in collaboration with many of its partners. To achieve support for CASSINI in Stratum, we had to do two things. First, we added support for the open config models, specifically the optical open config models, to the GNMI server implementation running in Stratum. Second, we added support for the CASSINI transceivers by using TIE, the transceiver abstraction interface from the TIP project, and we've integrated the TIE API into the Stratum platform manager. A lot of this work was done by PL Vision, Edgecore, and ONF. Thanks for your contributions. The second part of this integration was to run Trellis, ODTN, and ONOS on one cluster. The first thing we did is we added a new pipeconf driver for Broadcom to support Trellis. This is in addition to the pipeconf that we already have, which supports Barefoot ASICs. Second, we've added a new optical behavior to support OpenConfig models over GNMI for the Stratum CASSINI device. And lastly, we've run both the Trellis and ODTN apps together on the same ONOS cluster. This means that the topology, intents, flow objectives, and behaviors from the ONOS core are shared by both applications, and both application suites through the core and drivers rely on the same P4 runtime and GNMI southbound implementations. Next, let's talk about how Stratum supports Broadcom ASICs. First, we have a lot of common code. For example, the P4 runtime server, GNMI server, and GNOI server all sit on top of Stratum's common switch interface. Beneath the switch interface is where we do our adaptation to the vendor-specific ASICs and platforms. On the left side, we have the Broadcom node manager, which translates the P4 runtime entities into objects that are consumable by Broadcom's SDK. And on the right side, we have the chassis manager, which deals with port channelizations and configuration as a result of plugging and unplugging SFPs. All of this sits on top of a common Broadcom wrapper. To get this to talk to the ASIC, our initial open source project leveraged SDK-LT, and we had an implementation of the Broadcom wrapper that was SDK-LT specific. Now, we're pleased to announce an alternative implementation on top of Broadcom's OpenNSA SDK. And we have a Broadcom SDK wrapper now that talks to the OpenNSA headers. What does this mean for users? Well, from a user perspective, both SDKs are open source. And it means that users can choose whether they want to use OpenNSA or SDK-LT. And this is a choice made at build time. So when you're building your container using Bazel, you select either OpenNSA or SDK-LT for the target that you're building. OpenNSA supports a wide variety of ASICs from Broadcom, including ASICs in the Strata XGS and DNX family. For example, Trident 2, Tomahawk 1, 2, and 3, and Qumran AX. It's also a familiar SDK for current users of Broadcom silicon. On the other hand, SDK-LT supports Tomahawk ASICs and Trident 4 ASICs. It pairs nicely with Broadcom's NPL and is their next generation SDK for users that are looking for something new. Either SDK is a good choice, and this choice now expands the set of ASICs that we support in the Broadcom family. Overall, we see a healthy support for Tofino-based platforms, Tomahawk-based platforms, and newly Trident 2-based platforms. Since we've open sourced, we've added 4 new platforms to the Stratum family. 2 are Tofino platforms from Stratus. We've added the CASSINI packet optical transponder from Edgecore using the Tomahawk Plus ASIC. And we've also added the AS6712 from Edgecore using a Trident 2 ASIC. Our new support for OpenNSA means that in the near future, we expect to have some additional Strata XGS platforms. Next, let's look at our demo topology. In the top right, we have a central office, which uses Edgecore CASSINIs as spines, and a variety of Stratum switches as leaves or top of racks as part of our central office data center. This central office has connectivity to the internet via an upstream router. This central office is also connected via long-haul fiber to a field office, where we have 2 more Edgecore CASSINIs acting as spines and a variety of Stratum switches acting as leaves. This is where access technologies such as fiber to the home, DOCSIS, or LTE could be plugged in. On top of both of these offices, we have an ONOS controller, which uses P4 runtime, GNMI, and GNOI to control the devices, as well as the Trellis and ODTN application suites. We can take a look a bit closer at the actual physical hardware, and we'll see that we implement this topology using 2 racks. The top rack is our field office, and the top 2 devices are the CASSINI spines. Then we have 2 Stratus switches, an Edgecore switch, an Inventec switch, and a server. The bottom rack is our central office, where we have 2 CASSINI spines, a Stratus switch, an Edgecore switch, a Dell switch, and a server. These 2 offices are connected using long-haul DWDM fiber links. These are the yellow links on the left and right-hand side of the screen. Now let's dive into the ONOS UI. As you can see in the top right, we have our central office, and in the bottom left, we have our field office. In this case, we can see the CASSINI spines, the top 2 devices in our topology. We can see the Stratus switch, the AS7712 from Edgecore, and the Z9100 from Dell. In the bottom left, we have our other 2 CASSINI spines. We have our 2 Stratus leaves, our Edgecore leaf, and our Inventec leaf. You can also see that we have hosts connected to each of our leaf switches. 10.0.1.1, 10.0.1.2 are our first subnet, 10.0.2, 10.0.3, and 10.0.4 are our other field office subnets. And in our central office, 10.1.1 is our first subnet, and so forth. Now let's use ping to explore connectivity between the hosts. I've logged into the first host in the bottom left. As you can see, its IP address is 10.0.1.1. And just for sanity, we can see that the host can ping itself. And the TTL for this ping is 64. Next, let's try to ping the other host in this subnet using Trellis's bridging functionality. As you can see, the TTL is dropped to 63. Next, let's try routing just in the field office. And you can see that we have access to 10.0.2.1, this time with 2 hops. Next, let's try pinging at higher speed and viewing the traffic in the ONOS topology. You can see that traffic is going from the first host up through the leaf, up through our first spine, CASSINI 4, and down to our second leaf. And packets are returning on the same path. Next, let's try pinging from the field office to the central office. And we can see here that we have connectivity, this time with 1 more hop, because we had to go through an extra spine and the DWDM long-haul fiber link. We'll increase the rate of the ping and view this traffic on our topology. In this case, you can see packets are now being hashed from the first leaf to the second CASSINI in the field office, to the second CASSINI in the central office, to the first leaf in the central office. And we see that there are 10 packets per second traversing this link. To make things a little more interesting, we can plug my laptop into our topology, specifically into the first leaf of our field office. As you can see, my laptop has an IP address 10.0.1.3. And from here, we can try first our bridging ping and we see that we have connectivity to the first host in our topology. We can also confirm that we have connectivity to the central office by pinging the first host in the central office. And you can see we're able to reach there. Let's start a faster ping and observe the traffic on the ONOS UI. In the ONOS UI, you can see that packets are going to the first host from my laptop across the right link and returning on the left link. We can also unplug my laptop to observe traffic stopping and then plugging it back in and observing traffic resuming. It takes just a second for traffic to resume while ONOS detects the device and reprovisions the path. Let's disconnect my laptop for now. Next, let's dive into the device view to understand a little better how this is working under the hood. As you can see, we have a list of all of our devices, including our spines and our leaves. Let's dive into our CASSINI and view the pipeline that ONOS is provisioning. As you can see here, we have a pipeline with many stages and tables. For example, we have the punt table used to send LODP packets and ARP packets up to the control plane. We have the MPLS forwarding table, which matches on MPLS label and is capable of swapping or removing that label. We have an IP forwarding table, and we have a layer 2 forwarding table. Next, we can look at the flows that are programmed against these tables. As you can see in the punt tables, we have rules for ARP, LLDP, and BDDP. We also have rules that are provisioned with the MPLS labels of the other leaf and spine switches in our topology, as well as a group to forward traffic to those tables. Looking at the group view, we can see all of the group entries, which will send traffic to the other leaves and spines in our topology. Next, let's look at one of the other Broadcom switches. Here we can see it uses the same pipeline as the CASSINI device with the punt table, the MPLS table, and the IP table. Looking at the flows for a leaf device is a little different. We can see the same punt rules, which send LODP and ARP messages to the control plane. But now we also see a lot of routes that are added, which take traffic from the hosts that are connected, encapsulate it in the MPLS packet headers, and forward them to the spines. Lastly, we can look at one of the Tofino devices in our topology. The pipeline for Tofino looks slightly different because the ASIC is slightly different, but the abstraction provided to ONOS is the same. Here we have a routing table, an MPLS table, a bridging table, as well as an ACL table, which is used to punt traffic from the switch up to the control plane for things like ARP and LLDP packets. We can look at the flows for this device, another leaf device, and we see that there are IPv4 destination routes, just like we saw on our Broadcom leaf. And in this case, we use a next ID to identify the spine or leaf that's targeted for this packet. Opening the group view, we can see, just like our Broadcom device, we use ECMP to hash across the spines. Lastly, let's look at the optical capabilities added by the ODTN applications. We can see the 4 CASSINI packet optical transceivers as optical devices. Diving into one of the CASSINI devices, we can see the ports that are available. In this case, we have an ability to change the target output power, and we can observe that that number will change in response. We can change it again and see that in real time, we get the current output power updated. We can also see the current input power. And going over to the CASSINI that's connected to our central office, we can observe that the current output power and input power match what we're seeing on the field office device. We can change the output power here and observe that in our field office, we'll have a new input power. We can also change the transmit and receive frequency for our DWDM transceivers. For example, setting a new frequency to 193 will update both the transmit and receive frequency. And we can see that the link disappears because the other CASSINI in our central office is listening on a different frequency. We can update the transmit and receive frequency for our CASSINI in the central office, observe a momentary drop in transmit power while the laser is retuned, and then switching back to our optical UI, we'll observe that now that both of the CASSINIs are using the same frequency to transmit and receive, the link is restored. That's all we had today on the Trellis, ODTN, and Stratum integration, and thanks for your attention. So that concludes our first overview and demonstration. The next thing we'd like to do is I'd like to invite Carmelo Cascone from ONF to talk about the use cases that are enabled by the P4 fabric, specifically Seba and the software-defined BNG. And just to remind, while Carmelo gets set up, if you would like to ask any questions about any of the content that you see throughout this webinar, feel free to use the Q&A button at the bottom of your screen to type your questions in. Thanks, Carmelo.
Thank you, Brian. So the next presentation is about Seba, ONF solution for SDN-enabled broadband access with disaggregated OLT and BNG. Before starting, I wanted to acknowledge the main organizations that are part of the Seba community. The demo I'm presenting today was made possible by their contribution. And big thanks goes especially to the 3 operators that are supporting and leading the project, which are AT&T, Deutsche Telekom, and Turk Telekom. So what is Seba? Seba is an open source platform for fixed broadband access, such as fiber-based access technology. The idea behind Seba is that of using SDN principles to disaggregate the appliances that are found in a traditional carrier central office. And so to bring the benefits of data center and cloud economies and to reduce CapEx and OpEx. To make this possible, first we virtualize the OLT and the ONU part of the access pipeline, and we do this with a software layer called Volta. The idea behind Volta is that of abstracting the complexity of the PON network and instead of offering a simple open flow switch-based abstraction. Second, we use Trellis to realize the fabric that connects the OLTs to the BNG. And finally, for the BNG part, we can reuse the same forwarding devices that are already part of the forwarding plane of the Seba pod to actually provide the same functionalities of a traditional BNG. And we do this using a project called SDBNG. Now I want to dive in on each one of these components to give a bit more details. So concerning Volta, the idea is that we can take a traditional chassis-based OLT, which has things like PON MAC blades that provides optical connectivity on to the subscriber. We find also backplane, switching backplane, and also compute blades to run the control protocol as well as management system. So the idea behind Volta is that we can disaggregate this big box using SDN principle. And so the forwarding plane is reduced to an OLT pizza box that contains only the PON MACs as well as a switching chip for the uplink connectivity. The Volta agent abstracts this box as well as the ONUs attached to it in the form of an open flow switch. Since we have now an open flow abstraction, we can use an SDN controller like Honos to control this device. And so we can run the control plane functions usually found in OLT like AAA, VLAN management, and multicast as SDN style applications. I should mention that Volta is a prominent project inside ONF, and it's already in path to production this year at AT&T, Deutsche Telekom, and Turk Telekom. Second, we have Trellis. We saw a brief introduction to Trellis in the previous demo, but it's worth to introduce it again quickly. So Trellis is a set of an SDN application running on top of ONOS that provide the control plane for a fabric that is entirely made of whitebox switches and merchant silicon. The nice thing with Trellis is that the same set of applications can be used to transparently control different topology. In the previous demo, we saw Trellis controlling a complex multi-stage leaf-spine fabric topology, and in this demo, we will see Trellis controlling a single switch, actually single leaf topology. In all cases, Trellis is specifically designed for Edge and FV applications. So the idea is that we want to forward traffic between some access devices like OLT and base station, down to some VNFs running inside some compute nodes, and then out to an upstream router that connects to a metro core network. The forwarding policy can be provided by means of starting routes using the Trellis APIs, or by integrating with an external router running traditional protocols like BGP or OSPF. And Trellis, again, is a carrier-grade solution, and as a matter of fact, it's already in production at Tier 1 operator in the US, like Comcast. The last piece of the Seba pipeline is SDBNG. A BNG, a traditional BNG, is a chassis-based box that is essentially a specialized router. The main function of BNG is that of routing subscriber traffic to and from the core network. So the BNG provides a number of specialized functions on top of basic routing, like subscriber tunnel termination for example, layer 2 access tunnels using double VLAN tags or QoQ, as well as a PPPoE. It also provides functions for accounting, hierarchical QoS, lawful intercept, etc. So similarly, as we did with Volta, the idea is that we can disaggregate this box into pieces using the SDN principle. So first, we have the user plane. The idea for the user plane is that we can use merchant silicon to provide the same functions provided in traditional BNG. What is more, we don't need new additional devices. We can reuse the same merchant silicon that is already available in a Seba pod. In the first implementation of SDBNG and in this demo, we're actually using two different chips. We're using an Intel Barefoot Tofino chip that is found in a fabric switch and a Broadcom X chip that is found in the OLT. The idea for Tofino is that we can program this chip using P4 to provide functions like routing, PPPoE termination, accounting, etc. While Qumran can be used to provide different function, which is hierarchical QoS. And that's because Qumran is especially designed for deep buffering application and application that requires advanced traffic management capabilities. I should mention that this design is based on an early contribution from Deutsche Telekom to ONF, and that other silicon options are possible. So we could implement the same user plane, for example, using other Broadcom silicon like Qumran 2C, or even SmartNICs. Once we have our user plane, we can think about the control plane. So the idea for the control plane is that we can take ONOS, the SDN controller, and abstract this many devices that comprise the user plane as one single logical user plane entity that can be controlled by our BNG control plane that can run either as a set of native applications running on top of ONOS, or the control plane can be an external entity that integrates with ONOS using some standard BNG CAPS API. Now, bringing everything together, I want to show you what the architecture of a Seba pod looks like. So on the left, we have the subscriber residence with the residential gateways in the ONUs attached to the PON network. And on the right, we have the core network, and we want to forward traffic between the two. So in the middle, we have one or more OLTs, and the fabric switches connecting the OLTs to the core network. Again, because we are using switching chips inside the fabric switch and the OLT to realize the BNG user plane, that's why you see in this picture the user plane being spread out between the OLT and the fabric switch. Then we have some compute servers where we can run our software stack. All the software components in Seba are containerized, and so we can use Docker to run them, Kubernetes to manage and scale them, and Elm to install everything. The first component is Volta, responsible for controlling the OLT. Then we have Stratum, which run directly inside the switch. And on top of these two agents, we have the SDN controller, which is ONOS. On top of ONOS, then we find three different sets of application. We have the Volt application controlling the PON and OLT side of things. We have the Trellis application in charge of controlling the routing, and finally the BNG control plane application for subscriber control. On top of everything, we have a last software layer called Network Edge Mediator that provides orchestration for the whole pod, as well as Northbound APIs for integration with traditional operator OSS and BSS. Before moving into the demo, I want to show you the demo setup and the demo flow. So in this setup, we have one Seba pod with one OLT and one switch, as well as two ONUs for two subscribers. We will call the subscriber Emma and John. We want Emma to be configured with a bandwidth profile of 200 megabits per second, and we want John to be able to access at 500 megabits per second. So given this configuration, how does an operator actually provision a new subscriber into a Seba pod? So we can do this by pushing some configuration using the NAM Northbound API. This configuration includes ONU whitelist as well as some subscriber information. The idea for the ONU whitelist is to tell the OLT for which ONU is okay to forward traffic across the PON network. While for the subscriber information, we need things like the VLAN tags used for the layer 2 access tunnel. These are usually called CTAG and STAG, as well as the bandwidth profiles. This configuration is then passed down into Volta, which configures the OLT with the CTAG and STAG flows, as well as the configuration for the traffic scheduler, providing the shaping capabilities to enable the bandwidth profiles. Once we have provisioned a new subscriber, then a subscriber can start the authentication phase. In this phase, a PPOE client running on a subscriber laptop starts sending packets like PPOE session discovery, authentication, and other control packets. All these packets are intercepted by the switch, the fabric switch, and sent to the BNG control plane application on top of ONOS using packetings. The control plane takes care of running all the control plane logic for the traditional BNG control plane logic and replies to the PPOE control packets. Once a session has been established, the Trellis apps and BNG CP app push down the necessary flows to enable routing of packets, as well as termination of the PPPoE tunnels. Once this is done, subscribers have connectivity to the internet, and this is realized entirely in hardware using the Seba pod fastpath. So packets for the downstream direction coming from the subscriber are received at the fabric switch with two VLAN tags and a PPPoE header. The switch takes care of removing this headers before routing the packets to the upstream router. For the downstream direction of traffic, we receive IP packets that are encapsulated with the necessary VLAN tags and PPPoE header before being sent to the OLT. So let's move now to the demo. Here we can see the hardware setup. We have one OLT, one switch, and one server, as well as two ONUs for the two subscribers. We have John, that has no access to the internet, and we have Emma, that also has no access to the internet. This is the NAM dashboard. We can take a look, for example, at the ONU whitelist. To start, I provided a whitelist for only one ONU, and this will be for John. We can see the serial number of the ONU that is whitelisted. Second, we can check the status of the OLT, and we can see the one OLT has been discovered by Volta. Then we can check the status of the ONU devices. So Volta currently discovered two ONU devices, but only one of them is in admin state enabled. And that's because of the whitelist. The other one is disabled. Second, we can take a look at the subscriber configuration, and we can see that we have only one subscriber, John, with a 500 megabits per second bandwidth profile. We can now do a connection test. So we go to John's laptop, and we use the standard macOS PPPoE client to initiate the connection. The client has been configured with credentials that are also configured on the BNG control plane application running on top of ONOS. We click connect, and we can see that the authentication phase is successful. An IP address has been assigned to the subscriber, and John can now navigate. We can also do a speed test and verify that indeed we have 500 megabits per second download, as well as upload. Now, since we configured only one subscriber, we do a different connection test with Emma. But since we don't have any ONU whitelist or subscriber configuration, this should not work. So we do the same thing for Emma. We open our PPOE client, We click connect, nothing will happen. And the reason is that since the ONU is not whitelisted, all these PPOE packets will be dropped, will not even reach the OLT, and so no reply will be provided. So let's provision EMMA. We can do this using the NAM REST APIs. Before doing that, we can take a look at the configuration file. Here we have a Tosca-based YAML file that provides the configuration for EMMA. We can see a specification of the bandwidth profile, 200 megabits per second, as well as the subscriber information. We can see the serial number where we want EMMA to be attached to, the serial number of the ONU, as well as the C tag and S tag that should be associated with this ONU. Finally, we also have an entry for the ONU whitelist with the serial number of the ONU. We can push this file using NAM REST APIs, and as soon as we do that, we should see that appearing in NAM. Indeed, now we have two subscriber entries, one for John, one for Emma, with 200 megabits profile for Emma. We can also check the ONU whitelist. Now we have two entries, one for John again and one for Emma. And we can also check the admin state for the ONUs. Before, one was disabled and one was enabled. Now they're both enabled. Finally, we can check the PPOE connection status. And we can see that one connection is approved, and we have also an IP address for that, and that is for John, while the other one is awaiting, and that is the connection entry for Emma. So we can do again a connection test using Emma's laptop. We'll click connect. In a little bit, we should see the connection to be successful. So authentication was completed, an IP address has been assigned to Emma, and now Emma has access to the internet and can navigate. We can also do a connection test, and we should see that indeed we have 200 megabits per second for download, as well as upload. The last thing I want to show you is how we do accounting in Seba. For accounting, the idea is that we can use some industry standards software like Kafka, Prometheus, and Grafana. So what we do is we collect stats such as pawn counters from the OLT and counters from the BNG user plane. We push these values into a Kafka bus. We use Prometheus to collect them, and then Grafana to visualize everything. So we can take a look at the Grafana accounting dashboard. We have one dashboard specifically for BNG, and we can see stats for each subscriber. We can see, for example, the total amount of data that has been downloaded in the last 24 hours, as well as the total amount of data that's been uploaded, and also the number of connections that happened in the last 24 hours. We can also see a time series of the traffic that has been sent and received by this subscriber, as well as the time series of the control plane packets exchange. In this case, we can see that after the connection of the subscriber, we have around 0.2 packets per second being exchanged, and that's because the PPOE client running on the subscriber laptop is sending one keep alive packet every 5 seconds. We can also see the same data for the other subscriber. Again, the total amount of downloaded and uploaded data, the time series of traffic sent and received, as well as control plane packets. To conclude, today I presented Seba. We should say that Seba and Volta are, again, prominent projects inside ONF. The current version of Seba, including Volta, is already in a path to production with 3 operators like AT&T, Deutsche Telekom, and Deutsche Telekom. And this version actually considered the BNG as an external device. The demo I presented to you today actually looks at the future of Seba, and we call this Seba 2.0. That includes the SD-BNG capability. We show how Stratum and P4 actually enable the BNG disaggregation. This is still work in progress, and there is some work to do. ONF is currently working into adding more functionality to the SDBNG, for example, HQS and other missing features, but we're also looking into adding support for a standard BNG CAPS API. This should allow integration with third-party control planes, BNG control plane, as well as support for other implementations of the BNG user plane, for example, using other merchant silicon option. This is the end of my presentation and demo, and thank you very much, everyone.
Thanks, Carmelo. The next presenter will be Abhilash Enderthi from ONF, and the topic of this presentation is bringing CI/CD to the SwitchOS platforms.
Bringing to S platforms. Networks have not kept pace with the speed of cloud development. They're effectively black box systems that are just expected to deliver packets. And the functionality of the networks is dictated by ASIC switch vendors, and bringing in new feature takes years. Now we have P4 and next-gen SDN interfaces, so networks can be enhanced at cloud-like speed. Network innovation needs to incorporate new CI/CD practices, best practices. This will result in accelerated feature development and deployment of Stratum. And also, it will provide a way to continuously certify Stratum-enabled switches to work with latest software releases. So, to have a good CI/CD framework, one integral part of it is the test framework. In Stratum, we are using TestVectors as a way to perform system testing. TestVectors is what Google proposed initially to build compliance tests for Stratum. TestVectors provide a way to build tests which are completely separated from test infrastructure, and they're able to define what a test verifies clearly. So most vendors can quickly adopt the test infrastructure to support the test vectors. These can be written manually or generated automatically. A test vector is defined as a set of test cases, and each test case is a set of actions and expectations. Actions are operations that are run on the switch sequentially or in parallel or in random order. And the expectations are the expected behavior as a result of the actions performed. So actions and expectations are basically a set of open API accesses like GRP, GNMI, or P4 runtime accesses, or external stimuli like data plane operations. We provide a reference implementation that compiles and runs the test vectors. We call it test vectors runner or TV runner. It's written in Go and takes advantage of the Go testing framework. TV runner takes test vectors as input and translates it into a set of gRPC requests and responses that go to the switch, and also the test vectors are converted to external stimuli like data plane packet IO. In most common scenario, there'll be a traffic generator that will send and receive packets to the switch under test. Traffic generator could be part of the TV runner itself, or it could be an external part. So this is our CI workflow. We have 3-stage pipeline for implementing CI/CD in Stratum: build, test, and publish pipeline. So whenever there's a new code change that comes to Stratum, we go the build stage starts. And in build, a Docker image is built for each combination of platform, that is Broadcom, Tofino, BMB2, for every SDE and kernel version that we support. all the images that are built in this stage are pushed to a private registry, and so apart from the building Docker images, we also run Bazel-based unit tests and static analysis in this stage. The second stage is running system tests on hardware and software targets. As I already mentioned, we use TestVectors to run the system tests, and we take advantage of the hardware available in the lab and run automated tests on the idle switches. Docker images that we built in the previous stage are used to start Stratum on the switch. With the help of TestVectors runner, we run TestVectors on each switch and use the results to publish the Docker images. The third and final stage of our CI/CD pipeline is publishing the Docker images. So if the build and test stages are successful, we publish the Docker images to Stratum project repository. After this presentation, we can see a demo of this automated pipeline. With the automated pipeline, we are bringing cloud-style agility to Stratum. Since the published Docker images have been tested and verified on multiple devices, they can be deployed in networks with higher confidence. ONF's new continuous certification program will enable supply chain vendors to embed their products for ongoing test and compliance certification with ONF's open source projects. As part of the certification program, the devices will be tested against latest master, as well as the historical data of the testing will be maintained. ONF will also publish a list of certified devices for each software release. For Stratum, we are currently recruiting founding vendors and devices. These devices will be included in our CI/CD CC pipeline, and it will be used to perform system tests. Results of the continuous certification process will also be published. Our plan is to formally announce the program in April or May. So for more details, you can reach out to Brian or me. Here we see three main jobs for Stratum's three platforms: Barefoot, Broadcom, and BMV2. Each of these jobs have three pipeline stages, as we discussed in the presentation. The build, test, and publish stages are triggered for each combination of SD and kernel version. Let's take a look at the build stage. The build stage of the pipeline triggers platform-specific build job. There are two stages. In the build, we build Stratum Docker image for SDN kernel version, and in unit test, we run Bazel build unit tests and static analysis. Once both build and build stages are successful, we move to test stage. Test stage triggers Stratum Barefoot test job. In this stage, we run test vectors on available switches. As you can see here, we have the started switch, which is being used in the other demo. So let's rerun the test vectors on the wedge BF switch. In the test job, there are multiple steps. First step is starting Stratum on the switch. So here we use the Docker image built in the previous job and wait for Stratum to come up. Second step is getting the test vectors and TV runner from the Git repository. Next, we push the pipeline config and set up loopback mode. In the next step, we run the test vectors. Currently, we run some semi-automatically generated GNMI scenarios and some end-to-end scenario where we subscribe to port counter, send a packet, and verify that port counters are incremented. We also run packet scenarios. Since we are testing in loopback mode, data plane packets that egress from loopback ports will be looped back as packet ins. So we are able to emulate ingress packets with packet out and egress using packet ins. Let's wait for the tests to finish. After running these tests, we do the cleanup. Once the build and test stages are successful, we run the publish job and push the Docker images to GitHub. As you can see, the Stratum publish job has been run an hour ago, and Docker Hub reflects the same, that the images, Stratum Barefoot images, have been published with the same timestamp. Along with Barefoot, we have same jobs for Broadcom, the build, test, and publish stages, and same thing with BMV2, build, test, and publish.
Thanks, Abhilash. So just a few topics to think about that we've learned today from this webinar. The first thing we'd like to talk about is how we have a pathway to convergence of Trellis, ODTN, Seba, and Stratum. Today we demonstrated Trellis, ODTN, ONOS, and Stratum, and we demonstrated Seba, ONOS, to a small extent Trellis and Stratum. But we definitely have a path to bringing all of these together into one unified solution. Going a step further, Ether is another example of a logical convergence opportunity for us. Another takeaway from this webinar is that P4 is enabling new use cases on commodity hardware, and SDBNG is built using P4 for the data plane and is a perfect example of this. And third, we'd like to point out that ONF's testing strategy will enable stable and rapid solution delivery, and that TestVectors enables or serves as a foundational building block for the continuous certification program for Stratum. So the first thing we showed is a field office and a central office connected by long haul fiber controlled by both Trellis and ODTN. And a logical future step or future work could be to take the PON, the ONUs, the RG, as well as the BNG and the Volta applications and run them all together on one ONOS controller for a complete solution. Looking forward, we wanted to provide links to documentation for all of the projects we covered today. For ODTN, P4, Stratum, Seba, TestVectors, and Trellis, here are some useful links that you might find for how to get started or how to learn more about the projects. And as a next step, I would encourage you to download the code or a pre-built Docker container, send us an issue or a pull request if you want to make an enhancement or fix a bug. I'd also encourage you to join the mailing list, the Slack workspaces, and the TST calls for each of these projects. And lastly, if this is new to you, I'd encourage you to try a tutorial. It'll help level you up and get you started to understand this technology firsthand. So with that, we have a few minutes, and we'd like to open the floor up to questions to any of our panelists. Please use the Q&A button in the bottom of your screen to ask a question, and we'll read the question aloud and then answer it. So while we're waiting for questions to come in, we can maybe address some questions that we had from the first webinar yesterday. So one of the questions that we had was around some of Broadcom's newest ASICs, like Trident 4 and Tomahawk 4. And the question was, when does Stratum plan to support those ASICs? The good news is that both with OpenNSA and for SDKLT, we've got two distinct SDKs that give us a lot of flexibility for bringing these boxes in. The real limiting factor right now is for the vendors that have these boxes to either lend one or give access to one to the Stratum community or build support for those boxes themselves. But we see no limitation or roadblocks for supporting those devices in the future. We've got another question from someone out on the webinar about deployment plans for Stratum plus CASSINI. So with respect to deployment, it's worth noting that this is really just the first attempt at getting Stratum working on CASSINI. We haven't yet run it through qualification paces for a production deployment. However, this first milestone step does enable us to start looking at production opportunities for Stratum and CASSINI. We're working with both the ONF communities as well as the TIP communities to find some opportunities, but I can't speak to any of those concretely at the moment. Another question we have from online is this presentation available? The answer is that all of the presentations and demonstrations that we'll be doing as part of this webinar, as well as the entire webinar video, will be made available on the ONF website and sent to participants after the call. Earlier today, we also had a question about the continuous certification program. And the continuous certification program has not yet officially been announced by ONF, but as Abhilash mentioned, we are planning to recruit members for Stratum and a few other target devices in starting from now and over the next few months. Those will be the founding devices and the founding members of the program. So if you do have hardware and you are interested in joining our continuous certification program, please do reach out to us. And if you're interested in learning more about it, we plan to have an official press release and an announcement and website available in the next few months. I see one of our participants has raised his hand, so let me try to allow him to talk. Hiroshi, you can ask your question now.
Yes, can you hear me?
Yes.
Okay, thank you for the presentation. I have a question about the test vectors. Is this used in TIP project?
Sorry, could you repeat the last part of your question?
Is the test vectors used in TIP project? Because there are some collaboration between ONF and the TIP project.
I can try to give a first answer, and Abhilash, you can answer after this if you want. So TestVectors today I'm not aware of usage outside of the ONF community. That doesn't necessarily mean it's not happening. TestVectors are a great way to define stimuli and expectations for both P4 runtime and GNMI, as Abhilash mentioned. So I think it would be great for the TIP project if they wanted to create test cases around validating GNMI, or, for example, the optical models, but I'm not aware of a usage there yet.
Okay, thank you very much.
Abhilash, did you want to add anything? Okay. Any other questions? You can either type them in or you can raise your hand and I can give you talking privileges. So a question comes from someone online. Do you know if Stratum is deployed in Google Data Center? Unfortunately, ONF isn't able to comment on the status of Google's deployments at this stage. But we can say that the original source code from Stratum does come from the switch operating system that Google had developed internally. And the goal from Google's perspective was to give this to the community so that they could, the community could develop support for Stratum on whiteboxes, as well as further the adoption of P4 runtime and GNMI and GNOI in the community, ultimately with a goal of once that becomes stable, starting to consume it. So you'd have to reach out to Google specifically around their deployment status, but the Stratum code does come from them originally. There's another question online. Do you have any plans to support new whitebox packet transponder hardware? And the answer to this question is absolutely. But really, this is going to be something that needs to be driven by the community. So with CASSINI, we had TIP, Edgecore, Lumentum, and PL Vision that all approached ONF and the Stratum community and said, hey, we really want to put Stratum on these boxes. How can we do it? And the ONF worked together with them on the architecture and qualifying the implementation. And so if you've got another white box packet transponder that has a merchant silicon ASIC or not in it, we already have the TIE integration done. So if you already work with TIE for optical, great news. And then depending upon the switching ASIC, if any, that's part of your packet transponder, we would just need to make sure we have an integration for that as well. So I guess the answer is we would love to have another packet transponder, but we don't have any immediate plans or community interest to do so. If you happen to have one and are interested in doing that, please let us know. We probably have time for one more question, if anyone has one. Well, thank you very much, everyone, for attending today's webinar. Thanks for your time and your attention. And if you have any other questions about any of the topics that we've presented, feel free to reach out to any of the presenters or the mailing list or communities that we represent. We'd encourage all of you to join us in a lot of these initiatives. These are open source initiatives and community driven. And it's members like you that really help us to make progress in these areas. So thanks again and have a great rest of your day.